my first time at SATURN, so it's a very different community than the ones I'm normally involved with and speak to. So I'm quite excited to be here, and it's really nice to meet so many new people, first off. Including, actually, we published, or just this week, there was a special issue of IEEE software published with on microservices, and one of my co-authors, are you in the room? Priyan? No, he's not. Okay, well, anyway, one of my co-authors is here as well, so it's quite exciting. So I've got an hour and a half to drivel on about evolutionary architecture, and I propose to do that via the mechanism of storytelling, mainly because I think stories are immensely powerful, but also important, and I think it's important that we tell each other stories about the things that we've done. There's some theory in here as well, because I need to set some level with how my brain works, which is strange, to say the least. So there's a bit of theory in here, but mainly I'll be telling a few stories about things like space flights. There's some wizards. There's even some software architecture, you'll be pleased to know. So obviously Rebecca yesterday sort of introduced the topic, introduced her thinking, Neil's and Pat's thinking, and in general, I guess, ThoughtWorks' thinking on what evolutionary architecture is all about. So I'm going to try and give some practical examples about how I've sort of run projects, or a program in particular, using these techniques. Because we've been doing this sort of stuff without really having a name for it for years and years, as I'm sure many of you in the room have. So I called this talk, Betting on Software Architecture as Code, a note on hypothesis-driven architecture. And it's a bit of a mouthful, I appreciate. But I'm going to unpack this, each word, in fact, over the course of the next hour and 15 minutes or so. So the first thing I'd like to get out of the way, and again, something that Rebecca mentioned yesterday, is what is software architecture? So this is my definition that I'm going to be using. Software architecture is those decisions which are both important and hard to change later. It's the hard stuff, it's the difficult stuff between our software systems, if you like, or underneath our software systems. I should have had a caveat, because when I was looking into the provenance of this quote, it could have been Ralph Johnson who said this. Martin's a bit unclear. He thinks it might have been Ralph, but he's certainly said it as well, so I'm just going to call out both. So what are the things we normally consider to be hard to change? There's lots of them, and many of them are related to the software quality attributes. Did I get that right? Yes, I got that right. Good, that's what I should be using. Software quality attributes, but I'm just going to call out a few things that I think are I've found traditionally hard to change once you've got going on a program product. So things like programming languages, domain application protocols, process boundaries, integration protocols, hardware environments, and your deployment topologies. Now my hypothesis actually is in the last few years, 5 years even, that quickly, a lot of these things are no longer hard to change. And that's a bit bizarre. And that, I think, allows us to do much more stuff, much more easily and much more quickly, and to take advantage of what Rebecca was saying and was describing yesterday, is the fact that market conditions are changing so rapidly, consumer preferences are changing so rapidly, obviously for a given class of software system. So why do I think that, for example, programming languages are easy to change? Well, this, I think, is related to the movement towards building smaller things. Fundamentally, if we're building things that we can throw away, and that's one of the principles behind, I guess, microservices, is building small things that we don't rewrite, we can throw these things away. Then when we do that, we can make another choice, a different choice about the language to program that thing in. So I like Chad Fowler, who's obviously very well known in the Ruby community. He was CTO at Wunderlist, before it was sold to Microsoft. And he had a nice idea at Wunderlist where you could build your microservice using any technology you wanted, any language at all. And in production, they had microservices running in Clojure, in Haskell, in Ruby, in Python, in Java, I believe Scala. Pretty much the whole gamut of, quote, modern software, or modern programming languages, unquote. But they added some constraints. And this is also important, I guess, when you're offering choices to people. And the constraints they put in place around their teams was you can choose anything you like, but it must be readable to someone who doesn't understand that language. So if you print it out, you must be able to read it and understand it, understand what it does, its responsibility. And the second constraint, after being readable, was it must be rewritable in half a day. Well, that's, if you think about it, that's pretty extreme, right? When you're talking about building software systems composed of these very small services written in anything which can be thrown away, that's pretty extreme. But it does lead to the me to the conclusion that actually things like programming languages, technologies that we use to underpin our software systems are actually becoming more and more disposable. Process boundaries, well, with microservices, it's very common for teams to split services or to merge services. So process boundaries are no longer something that are necessarily static and fixed. In fact, they morph over time, and they should morph over time as we learn more. For example, I might create a service to perform one particular task, another service to perform another particular task, and realize that actually they should be the same thing, because potentially I might have to create a distributed transaction across them. Now, we don't like distributed transactions, they're hard. So in that case, I would suggest maybe putting these things together. So process boundaries can morph over time. And this is part of the movement towards things like building products, not running projects. Funding long-lived teams incrementally over time, and giving them the option to do whatever they want within their team boundary. So if I want to replace a service, I can replace it. If I want to merge services, I can merge it. So things like process boundaries are becoming more amorphous. Integration protocols, always going to be hard. Domain application protocols, always going to be hard. We're always going to have to think about how we're communicating between these processes. Well, always I would suggest, the way I work with my teams, is to agree collectively up front the domain application protocol, what we're going to use to communicate. But then what about things like hardware environments, deployment topologies? This has undergone a massive shift in the last couple of years. Now that we're building or starting to build cloud-native applications, I guess, let me back up a bit. Now that we're starting to look at the cloud first rather than on-premise first, and that is a thing that appears in the last edition of the Technology Radar. CIOs and CTOs are now saying, why should I build stuff and deploy it on-premise? Why not the cloud? For various reasons, not usually, I should say, cost. It's not normally a cost play anymore. It's a flexibility play. It's a scaling play. It's a realization that actually Amazon, Google, and Microsoft have got some really, really, really good engineers running this stuff, right? So people are looking at cloud first now, which means things like our hardware environment and our deployment topologies, if we're running in the cloud, also become easy to change. Well, this is kind of a revelation. This was a revelation to me. Things that are fundamentally hard have become easy, right? And quick. Now, I can change using a technique I'll come to later called Phoenix environments. I can decide, if I'm in the cloud, to tear down my entire production stack running in Europe and bring it up again in North America. And it takes a few lines of code to do that, which I can push through an automated build pipeline, and some tens of minutes later, I've got an entire replica of my production stack in a completely different geography. That's extraordinary that you can do these things. But the implications of doing these things, I think, are what the rest of the talk is about, of making these things easy to change. So that's really what this talk is about. What are the consequences of making, for example, programming languages, process boundaries, hardware environments, and deployment topologies easier to change? I'm going to take a little step back from that to start, and I'm going to ask a question of us, of the room. And that question is this: how do we usually make decisions about the things that are hard to change? And I'm not in Scandinavia now, so I'm actually expecting an answer from the room. So you sort of build up and build up and build up and build up, and then suddenly you have to make a change. Yeah. Not alone? That's, in an ideal world, it wouldn't be your ivory tower folk making these decisions, yeah. So that prevents us making a change if the cost of change is too high, yeah. And that can happen as we, I guess, progress over the course of a program of work, or 20 years into legacy business as usual. What about when we start projects? When we start building products?
Maybe we run an experiment and see if we can make our architecture do what we want on a small scale, making a better map, and if it works, then we know, and if it doesn't, then we also know.
So you can all go home now. I mean, that is actually a valid option. My experience, though, has been that most decisions about things that are hard to change are taken by people with a bit more experience. Say, maybe I've got the grey beard. I'm like a grey beard times 2 because I've been in the industry for over 20 years. Plus, I actually have a grey beard, so this is kind of like doubling up on the grey beard thing. So being a grey beard, I've seen some stuff, as I'm sure many of us in the room have. We've been through the process of starting projects, of building software many, many times. And that's great, right? Because that experience really helps us make decisions about the things that are hard. But it comes with a caveat, which is all the biases that we build up along the way based on our experience. This thing worked, so therefore I'll do it again. And sometimes we do that in situations where it's not appropriate. So things like survivorship bias become apparent. We also, I think as you get a bit more experience, you start to do things based on your gut, right? This feels wrong, or this feels right. And again, this is actually a good thing. This is a good thing. And actually, if you go back to something called the Dreyfus model of skill acquisition, making decisions based on insight and on your gut is actually an indicator of being fairly high up on the Dreyfus scale. So the Dreyfus model runs from novice through advanced beginner, through competency, through proficiency, and through expertise. This is the famous 10,000 hours to become an expert idea. And the higher levels, the proficiency and expertise, they're characterized by making decisions based on gut feel. But of course, how do you distinguish gut feel based on insight from survivorship bias? So some difficulty sort of untangling some of this. And then we often make decisions about software architecture up front. And I don't think anyone in the room is going to sort of say they've never been in a situation where at the start of a project, a bunch of smart people have sat down and thought about things for ages and then said, now do this to another group of people. We've got some nice diagrams. Fortunately, I think we're beyond the point now where UML diagrams, class-level UML diagrams get handed over, I hope. Maybe that still happens in some places around the world. But we often fall into this trap, and I think it is a trap of spending a lot of time up front with smart people in a room thinking about stuff and then throwing stuff over the wall. Oftentimes up front. My experience with the upfront thing is it's a sticking plaster in general. When I go into organizations and they have these big architecture boards and all decisions have to go through the architecture board before it gets passed down the line to get built. That looks to me like scar tissue, if you like. It looks to me as if sometime in the past something bad happened, they were exposed to some risk, or maybe there was maybe a risk manifested, and maybe a website went down, or a critical system went down on Black Friday, or something. Nod to Nygaard in the corner. And so what we do as humans is say, how do we manage this risk? Well, what we'll do is we'll do more thinking about it up front, because if we thought about it more, this would never have happened. So we sort of fall into this trap, this self-reinforcing trap, this positive feedback loop of adding more and more scar tissue onto our processes on how we make decisions about technology. And that's completely understandable, it's human nature, but it's worth looking out for. Okay, so my idea is that we should be able to make decisions differently, especially given the things that were hard to change have now become much less hard to change. So can we make decisions more systematically, fundamentally more cheaply, and what would that look like? That's the question. I should basically take a step back and explain who I am for a start, because at the moment you've got no idea at all who I am, apart from the fact that I know a few of the Norwegians in the room. So my name is James Lewis. I'm a consultant at Thorwix. I've been there about 12 years now. About 12 years. We publish a bunch of stuff. We feel it's really important to give back to the community, which is one of the reasons that ThoughtWorks would, for example, support me coming here and talking to you, to share our experiences both in print format and also by speaking at these sort of events. And I guess I'm most famous for value of famous, for going on to a sleepover at Martin Fowler's house and writing this definition of microservices. Okay. So I mentioned at the start that I'm going to tell some stories. So this is going to be the running story throughout the book. It's a book what I wrote. I'm really proud of this book. And this is the book. It's called The Endlessly Bifurcating Trousers of Reality. And if anyone's come across Terry Pratchett, the author, this is heavily inspired by some of his observations about how time works and the time monks. So what is the endlessly bifurcating trousers of reality about? Well, it's a story I wrote about a project I was on, fundamentally. It's in retrospectively, but it's the story of a project to build or rebuild a sort of $3 billion a year revenue scientific publishing platform. So given that there's a lot of academics in the room, I'm hoping that this will resonate with some of you. For those of you who write papers for a living, you know the process. There's lots of copy editing back and forth and reviews and peer reviews, and then finally everything gets agreed, and essentially what happens internally is a massive dump of XML gets pushed somewhere and then displayed somewhere else. And the thing that displays it for this publishing company was worth $3 billion a year, which is, not bad. And they had a system which had been running for about 15 years. It was a C++ service-oriented C++ system based on a service-oriented architecture. And again, 15 years worth of $3 billion a year, that's pretty good investment. If I build something that lasts that long, then I'd be quite happy with it. But it sort of come time for a replacement to be built. They weren't able to take advantage of various things, which I'll cover in a sec. So we're going to start reading this story. I should point out, it's a very particular type of book. I'm a geek, unashamedly so. I paint tiny figures for pleasure, like little Warhammer figures. I play computer games. And I do things like play board games and occasionally role play. I'm sharing a bit too much now, I can tell from the faces of the people. Where the hell is this going? Well, it's going because this book is a very particular type of book. It's a book called a Choose Your Own Adventure book. If you've come across those. Who's come across Choose Your Own Adventure? That's maybe a third of the room. So these were really popular when I was about 8 or 9 in the UK. So probably sort of early 80s time. And the idea behind Choose Your Own Adventure is it's a sort of gateway drug to Dungeons and Dragons. In fact, that's exactly what it is. The idea is, at the start you choose a character. Maybe I'm a warrior or a mage, depending on the book. And I roll my stats. I roll for my charisma and my strength and that sort of thing. And then as I go through the book offers me choices about what to do next. So it might be that I face a dragon and I have a choice to cast a spell, or I have a choice to run away, flee, if I can't cast a spell. And you progress through the book and try and beat it. Of course, what everyone does is keep their thumb in the book, so you look forward and then you say, but that's giving the game away, I think. The nice thing about, if you think about this as we go through it, it's also restful. There are links in this. This is level 3 rest compliant, if you like. So, the endlessly bifurcating trousers of reality. History. The lawful good product owners of the publishing house had long lived in awe and fear of their publishing systems. In awe, for they had made a tremendous amount of gold, but in fear of the time taken to change them, their slowness and their fragility. A messenger was sent to fetch help from a distant land famed for its mighty wizards. You have taken up the challenge. This is setting the scene, right? So this is the publishing house. They've built this platform. They had this platform for 15 years. Unfortunately, it's become unmaintainable, more or less. They can't add new features to this platform at the rate at which their users demand. So pace of change is incredibly slow, cost of delay too high. Let's see what happens next. You must save the product owners by rebuilding their website. You start off the project. In the course of discussions, you discover that your goals are threefold. You must, 1, improve availability, 2, improve performance, and 3, reduce cost of delay. An enterprise architect approaches and addresses you. You may use summon walking skeleton, turn to page 4. Or you may cast analysis paralysis, in which case you turn to page 3. If you have none of these, you will have to draw your sword and fight. Turn to 178. I'm going to unpack these goals here. So, there's an interesting thing with the business model for publishing houses, right? Fundamentally, their stock market price is linked to the number of people who click on links on a page. Right? So every time someone downloads an article from a journal or from a book or whatever it is, essentially they register that, and literally the CEO will report those numbers every quarter to the markets. But fundamentally, their stock market price is dependent on people clicking links, which you can see ties nicely into number 1. The more you are up, if you're not up, people aren't clicking links, therefore you're not making money. And it really is as simple as that from their perspective. Again, there's lots of academics in the room, so open access, that's the right term, isn't it? That's a thing. This is not that shop. This is very much a money-making shop. So the more they're up, the more money they make. Also, performance is linked to that as well. Turns out China is a thing now. Turns out Australia finally has internet as well, which is great. They don't have to rely on the Tuesday internet drop via USB sticks anymore. But the old platform wasn't able to actually serve users in China, in Australia, without being ridiculously slow. And by which I mean 15 plus seconds to load any page slow. Which of course means people aren't clicking on links, which of course means they're not making as much money as they could. And finally, reduce the cost of delay. So we want to be able to provide a better platform for both content authors, so academics writing papers, who want their papers to be displayed exactly as they've agreed with their editors, but also researchers using this site as a resource. I should point out that we didn't come up with this out of the blue, and this ties back into what Rebecca was talking about yesterday with fitness functions. Now, we didn't explicitly talk about fitness functions back then. That's quite a new thing that Rebecca and Neil and Pat have sort of described in their book. But what we did talk about, and I apologize for blaspheming again, in this hallowed room, but we did talk about something called cross-functional requirements, which were based on software quality attributes. And so this is typically the sort of thing I would collect at the start of a big program of work, collaboratively with a bunch of people. It's pretty low tech, right? It's a spreadsheet. We've got a bunch of software quality attributes down one side, and then we've got a number of columns which describe what we're going to do about these cross-functional requirements, to meet these attributes. And so we have things like a score, which I'll unpack in a sec. We have a type, which I'll unpack in a second. And then we have a plan, and the plan is to move one step up the maturity model. It's a classic maturity model with layers from 0 to 4. And then we have some notes. So I quite like this archiving plan. Andy goes away and finds out about this stuff. This is very early on in the project that we were talking about this. We were using this type of thing. These are the levels, if you like, that we use on a cross-functional in this maturity model. So one is basically WTF, we've never heard of this, what are you talking about? 2 is this is a new thing. We don't know what it is, don't really have much understanding of the requirements, but we know it's something we should consider. Number 3 is requirements are understood. We know enough about what we need to do to meet this requirement. 4 is measurable. We've got hard numbers that we know. And 5 is actually demonstratably meeting those requirements. So either through automated or manual processes, manual testing, I can demonstrate to my stakeholders that we are meeting these requirements. You can see where this ties in to the idea of a fitness function. Essentially, a fitness function is when you're able to articulate your requirements to the point where they're measurable, and then able to test them either manually or in an automated way. The other thing on this spreadsheet that's quite nice is, so that's what the score is here. The idea is to push the score over time. But we also have a type. So how are we going to meet? How do we think at the moment, at this point in time, how are we going to meet these requirements? So in some cases, it's going to be through actually playing user stories. We're an agile development shop, small a. So we'll write user stories, and they'll go into our team's backlog. In some cases, it's design principles. In some cases, what else have we got? It's acceptance criteria on every piece of work that flows through our teams. So it's basically a way of capturing both the things that are important to us and how risky and stuff they are. And generally, we have a visualization like this, right? So it's pretty straightforward. Essentially, what we're saying is stuff up here in red we don't know enough about, right? But we also know it's important. So this is really risky. And what we want to be doing over time is pushing this down here. So we need to know a lot about it so that we can test it. And pushing it from there or across. And I don't usually have that graph on my wall. Normally I'll just have a big sheet of paper with some post-it notes. And every couple of days in the stand-up, or maybe it's every week in the weekly stand-up, we'll just talk through, okay, so what are we doing with this? How worried are we? How quickly do we need to move this? It's an architecture conference. Look, there's an architecture. Awesome. So this is what the idea that we started with for building this publishing platform. I've redacted some information. It's pretty straightforward, really, and this isn't what we ended up with. We'll see that in a bit. But the idea was pretty straightforward. We had a bunch of sort of third-party and/or legacy services that were sitting somewhere in the world that we had to use. So things like access and entitlements, usage services, content metadata services, Scopus, which will be familiar if you're in academia. And inside this dotted line were the things we were going to build. And you can see there was kind of a pattern we decided on, which is whenever we need to talk, or generally whenever we need to talk to an external service provided by someone else, we'll put a facade over that so we can control the rate at which that API changes. We can control at least its quality attributes. So this is the web page at the top. We had some form of article rendering, and it was going to use a whole bunch of other services in order to render a page. As I say, we didn't end up with this. But this is where the article store, S3, this is where all of our raw XML content was going to be. Everything just, actually terabytes of XML just dumped into S3. Yeah, so a bit of that. Back to our story. That's a bit of context for you. What should we do? Who's familiar with a walk-in skeleton? Yeah, maybe it's worth unpacking what a walk-in skeleton is. So the first time I heard this was in the book Growing Object-Oriented Software Guided by Tests by Nat Price and Steve Freeman. So they're the people, they're the two folks behind JMock, the popular mocking library for Java. Who knows what Java is? Sorry. I was about to do some terrible explaining to you. So they talk about the idea of creating a walk-in skeleton as creating the thinnest slice through your architecture possible, vertically through your architecture. So in this case, it would be the thinnest slice through the user interface, rendering, and S3 in order to display an article. But crucially, being able to then push that all the way through into a production-like environment. That's the important bit. It's not just having a thin slice that you can say on your development machine, look, I've got a thin slice. It's I've got a thin slice with tests that's production ready, and I can push that through a build pipeline in an automated fashion into a production-like environment. So that's a walk-in skeleton. It's a typical way on small A agile projects or XP projects to get going quickly. What's the smallest thing I can do to prove value? So what should we cast? Summon walk-in skeleton or analysis paralysis? I think we should cast analysis paralysis because, we would like to make decisions up front, right? So this is, if we can push this off for 6 months, That'll be great. So we'll go ahead and click on the link, turn to page 3. You cast analysis paralysis at the enterprise architect. Foolish young adventurer, says the architect. We follow the evolutionary school of architecture, and we shall have none of the lawful evil ways of waterfall. The last thing you see before everything goes dark is the architect incanting in a strange voice. You have died. Turn to page 1. Oh dear. Let's turn back. It's a good job we had our thumb in the book, right? You can just flip back. Turn to page 1. Okay, so let's cast summon walk-in skeleton. Your walk-in skeleton coalesces in a cloud of noxious gases and solidifies as a Java drop wizard application. You reach into your backpack and deploy the content store. Your walk-in skeleton reaches out its skeletal arms and grabs armfuls of raw XML. Would you like to transform the XML inside the skeleton, in its ribcage presumably, or would you like to use a magic box? So this is the walk-in skeleton. We've got this really thin slice based on Drop Wizard, Java framework, lightweight Java servlet framework. And at the moment, it's just able to go off to S3 and pull back some XML. Of course, what we need to do is to display a different type of XML, which would be obviously HTML, because it turns out users don't really like reading XML straight. So what should we do? Transform the XML inside the skeleton, or should we put something in here between our little rendering library or process up here and S3 where our XML is? Use the magic box. Yeah. Microservices. Woot. I'm actually going to back up from this, because this is where I start. This is where you start to see inside my head, which is the terrifying bit of this talk. Because I've started to see over time decisions like this as being these sort of forks in the road, right? So it's kind of I lifted this from from the interwebs, from a site on evolution, essentially, biological evolution. So this is a divergent evolutionary graph. That's the technical name for it in biology. And I've started to see decisions that we make on our software projects in this sort of way, right? So we've got this future that's stretching out. The bifurcating trousers of reality stretch out in many, many different directions. The solution space covers all of this stuff. And every time we make a decision, we are narrowing that solution space. We are closing down options. This is how I see building software, designing systems, building systems, making choices about what we do next. Let me see if I can illustrate this, right? So we've got two options that we can take after our walk-in skeleton. Transform content within the walk-in skeleton. Right? That's one branch we could follow. Another branch is to use another service, a microservice, the magic box, to transform that content. Now initially, they're going to have similar effects. Modulo going over the wire a bit more. But on the one hand, you can imagine leading to a distributed system, one evolutionary path leading to some form of distributed system, microservices architecture, and reductio ad absurdum. The other path, if you take that path, leading to a sort of monolithic, hopefully well-structured monolith, but with everything happening within the same single process. So this is, I know, my inside of my head is scary, right? So this is the question: how do we decide what to do? How do we decide which of these branches to follow? Which areas of the solution space that do we want to keep open? And how do we do that in a way that we keep as many of those options open as possible? I said I'd unpack the title of this talk. Betting on software architecture as code. So I'll talk a bit about betting now, right? So what is betting? You kind of a conference talk without at least one dictionary definition. So betting, the act of gambling money on the outcome of a race game or other unpredictable event. Now, there are a lot of people who tell me that building software is predictable. It's reducible, that you can reduce the act of building software down to a series of small steps, essentially. And then when you line them all up, you're going to be able to know the outcome. Essentially, this is like Gantt chart time, right? I don't think building software is a reducible process. I think it's irreducible. I think because it's a complex adaptive system containing people and organizations and new requirements and adapting to customer demand, I don't think it's possible to do that. I think it, in fact, is basically unpredictable. And therefore, I think we're going to be able to bet on these unpredictable events as we build software. And this is kind of how I think about evolutionary architecture. It's about placing small bets, spending small amounts of money, Harold, who's mentioned this at the start, spending small amounts of money on a number of different options, or deciding to spend money on different options. So evolutionary architecture, in my mind, allows us to place small bets and then reevaluate our decisions based on outcomes, small decisions. And this goes back to things that were hard to change at the start of this talk. When things are hard to change, we end up placing big bets. It's hard. I have to invest a lot of money in changing the location of my data center, say, or the programming language if we've got a big thing, for example. But if we keep things small, and if we take advantage of modern technologies, then we can place much smaller bets, which means we have more options. We keep the options open. Whereas I would argue that upfront design, we bet the house, right? It collapses all those options down to a single one. We bet that the stuff that we've thought about now is right, and we're going to go charging ahead till we reach our outcome. So, evolutionary architecture is about small bets, keeping options open, for me. Upfront design is about betting the house. Now, I know what you're thinking. You're mad, A, and B, this is kind of cool and kind of new and stuff, but I would argue that this isn't new. I would argue that this goes back a long way. We have a long history, especially in this country, of extraordinary achievements based on this sort of idea. And so I'm going to talk to a couple of them now. We're going to go back to 1961 briefly. Woo! I'm going to ask this question. What did the Gantt chart for the Apollo moon landing program look like? I've drawn one up, not to scale. Maybe it looked a bit like this, right? So we've got design the Saturn V, but build the Saturn V, launch it, zoom through space, land, tea and biscuits. Who thinks the program to land on the moon looked like that? Right answer. So, looking in terms of this sort of divergent evolutionary graph, this is the idea that we've got President Kennedy's speech and you've got tea and biscuits at the top, and there's this like, boom, we're going to go this direct line all the way from one to the other. But I would argue, and what the engineers at the time knew, that one does not simply walk into Mordor. Why is that? Well, it's because literally at the time, people didn't know how to do a whole bunch of stuff that was necessary to get to the moon. Like, it had never been done, clearly. This was primary research going on, primary engineering. Some examples. Can humans survive in space long enough to get to the moon and back? No one knew, right? No one knew if humans could survive for 2 weeks in space. Can we dock one spacecraft with another spacecraft? Never been done. Seemed like an insurmountable problem at the time. Can we even get to the moon, right? I mean, computers at the time were not, I've got more processing power, much more processing power in my phone than anything Apollo had. Can we even get there? Orbital mechanics, difficult. And also, what on earth are we going to find when we actually get to the moon? I mean, are we going to be even able to land? Is it safe? And then how do we get people back? Because, the idea wasn't just to get people there. Ideally, we wanted to get people back. So how do we get the returning spacecraft to land? And the way they went about doing that is by running a series of experiments to address each of these problems in return. And this is my favorite one, which I'll cover first, which are the Ranger missions, which started just after. They were originally a bridge between, I think it was Mercury and Gemini, but they turned into something else. So the Ranger missions, 1961 to 1965, were a series of experiments to answer the simple question, can we even get to the moon? And so what they did was they basically launched a rocket, pointed it at the moon, and hoped it got there. And you think I'm joking about that, but that's actually what happened. And this is the description of those launches. Ranger 1 launched 23rd August, blah, lunar prototype, launch failure, didn't get off the ground. Next one, launch failure. This is my favorite, and you know, this is real. Missed moon. Just boom. It's nice, right? Totally missed it. Oh, actually, it's fine. This one actually impacted on the moon. That's good. I think one of these, even though it impacted, the cameras didn't work, so it was still a failure, but we'll come to that. Oh, yeah, spacecraft failed. It missed the moon again. Impact, cameras failed, so it was still a failure. And then 7, 8, 9, impacted, mission success. Tens and tens and tens, hundreds of millions of dollars were spent basically throwing darts at the moon, hoping we could hit it, just to answer that one question. The next one I'll just point out quickly, the Gemini missions. I won't go through all of these. But these were designed to answer the questions, how long can humans survive in space? So we've got a 2-person capsule. We'll stick 2 people in there, and hopefully they'll survive for 2 weeks. Yay. Can we dock one spacecraft with another? And how do we get that spacecraft to land at a pre-selected location? And the other series of experiments that they ran, or another series of experiments with surveyor missions, 62 to 66. And this was about, is it safe to land? Right? Can we find landing spots? There's another one actually as well. But can we find landing spots? Can we actually get to the surface? And all of these experiments were running in parallel. They were all about de-risking the actual process of getting humans there and back. It wasn't a linear progression. Design the thing, build the thing, execute the thing. And just to prove that they didn't, they had some very strange ideas at the time. This is something called the Regalo Wing, which was one of the options for how to land when you returned from the moon. It's a hang glider. This was one of the original set of tests, experiments they ran. So when the Apollo command, well, so the kind of cone at the front part of the command module, the lander, I guess, when that returned to Earth, it would deploy a hang glider wing and glide into land. This didn't work out so well. But this was tested on the Gemini missions. And of course, actually, they went with something else. They went with parachutes and landing in the sea, which is the path that led them forwards. So what did the Gantt chart for the Apollo moon landing look like? It was nothing like this at all. And my advice would be, unless you're Chuck Norris, you should probably do something similar. He simply walks to the moon, but yeah, we can't. We're not superhuman. I'm going to go back a little bit in time, back to 1945. Now, this is one of my favorite books of all time. I'm a geek. I'm a physicist originally. Honestly, it wasn't until I read this book, The Making of the Atomic Bomb, that I actually understood the history of nuclear physics. That's actually true. It's a wonderful book about a crazy period in world history with a terrible outcome, and the book doesn't shy away from the political ramifications at the end of the process. But it's an extraordinary journey through how Los Alamos came to be created, how the atomic bomb was built, and the journey that got there. I mean, if you think about this as in terms of human achievements, Apollo is an amazing achievement. At Los Alamos, on Friday nights, they would have 13 then Nobel Prize winners playing poker. Poker game was 13 Nobel Prize winners. It's one of the greatest concentration of human minds that's ever happened. But they didn't know things were going to work. They didn't have a Gantt chart. Again, this is a great quote from this book from General Groves. General Groves, had to begin building before he knew precisely what to build. They're talking about building the Lawrence, what's his name? Yeah, the Lawrence. I think it's now the Lawrence Livermore National Labs, but the process of electromagnetic separation of isotopes. Right? They had no idea how much they were going to need of these machines to do it. They had no idea how big the buildings were going to be. They had no idea how many people they needed to work on this stuff. But they had no option but to run experiments to work out what to do. So they started building. They went from the general to particular, from outline to detail. And in fact, there's an interesting thing happened on this program because they had multiple options for creating enough U-235 to power these bombs. There was gaseous diffusion, there was the electromagnetic mechanism, also there was the kind of nuclear pile that Fermi had been working on. So you have sort of gaseous diffusion. And actually, in this case, they ran both of these simultaneously. Niels Bohr has got this great quote when he arrived over from Sweden, where he'd sort of, the Swedes had rescued him from Denmark. When he arrived at Los Alamos, he said, I told you that you wouldn't be able to do this project without turning all of the United States into a factory. Oppenheimer said, yeah. He said, well, that's what you've done. You've turned all of the United States into a factory. At one point, just the gaseous diffusion plant used $300 million worth at that rate, 1945 rate, $300 million worth of silver from the US vaults, wherever they are. 300 million. Can you imagine being that project manager, writing that request form, like $300 million? And just to talk about quite how in the dark they were about what was going to happen. This is a quote just before the first Trinity test, the night before, about Fermi and he had a bit of a strange sense of humor, did Fermi. And it made some people angry and merely irritated others. I'd become a bit annoyed with Fermi when he suddenly offered to take wages from his fellow scientists on whether or not the bomb would ignite the atmosphere. And if so, whether it would merely destroy New Mexico or destroy the world. But incredible things were achieved by using particular sets of techniques, running experiments, concurrent set-based engineering, and so on. We'll fast forward a bit now to 2012, and then I'll carry on with the story. This is a picture of the landing procedure for the Curiosity rover back in 2011. It's a pretty complicated set of things that need to happen. And I was lucky enough to meet the principal investigator on this, a woman called Anita Sengupta, at a couple of conferences in Australia and the US. And she talked about the mechanism they used, the process they went through in order to successfully land the Curiosity rover on Mars. And the funniest part of this was when she was given a keynote at the GoTo conference in Chicago, and she finished the keynote, described the whole process, and someone in the audience asked, software engineers asked, so what sort of redundancy did you build into this process? And she just had like a moment where she just burst out laughing. I'm not sure if you were there, Michael, actually. You might, no. She just burst out laughing. Redundancy, she said, we can't put redundancy, we can't put an extra parachute in. Everything has to work first time. Because if you put an extra parachute in, that's extra cost in fuel to get it off the ground. It's extra space. We just can't do that. And they said, well, what do you do instead? Well, she said, we use this little thing called engineering tolerances. And everyone in the room, like 1,500 software engineers sort of went, sort of shrank a little bit into their seats. But that's pretty much what they do. It's not so much how to land on Mars, it's how do we test that we can land on Mars. And so everything is modeled, everything is simulated, everything is done in small scale, everything is done in recreations of Mars on Earth. You create options, run experiments in a safe way here before committing to the final thing. So what do these great endeavors have in common? So, they're high risk, pretty high risk, losing people, losing a war, billion-dollar spacecraft. They're hard to test, right? You don't want to lose people. You can't test sending people to the moon with people on it first. You need to send other missions before you do that. You can't use redundancy, and it's new science in the case of nuclear physics. And so looking at those individual things, putting a person on the moon, what did they do? Well, they created multiple parallel streams of work. They did rapid experimentation to solve individual problems. For the Curiosity, again, they used simulations, models. For the Manhattan Project, they used concurrent set-based engineering. They worked with imperfect information. They accepted that they weren't going to know what the future held. And they created models. In fact, the Monte Carlo model came from Los Alamos. John von Neumann created that, if you know that. So what I'm saying is, to overcome these seemingly insurmountable obstacles, they created options and ran experiments. They placed bets. So this evolutionary architecture thing, it's not a new thing. This has been going on at the heart of the most expensive, most high risk, most high cost, as I said, programs for decades. So just to drive that home, all of these are examples of options, placing bets for only the money we can afford to lose, or the lives we can afford to lose. And this is great at risk reduction, but it actually gets a bit better than that. It turns out options have value. If you've ever worked in trading, you might have come across this. Anyone got that? Black Scholes, absolutely. Yeah. You didn't win that award for nothing. Yeah, this is the Black-Scholes equation. And actually, there's a term in this here, which is the volatility of the underlying asset. And the fun thing, this is why, right, so everyone in the world is going, cryptocurrencies, oh, it's a nightmare. I've got like so many Bitcoin and the price is tanking and it's going up. And like, traders are loving this stuff, right? Anytime you get a volatile market, someone is making money hand over fist in the finance world. Volatility is a good thing as far as traders are concerned. As Rebecca said yesterday, does anyone disagree with the statement that things are more volatile in our environment, building software for users, than they've been before? Everything is more volatile, I would suggest. It is a more volatile market. And with more volatility comes more value. Options have value. And just to give you an example, this is the timeline from 2010 up to now 2017 of the ThoughtWorks Technology Radar themes. Can't see it on here, but around here was the first time containers appeared, Docker. I'm in a conversation pretty much every week with a CTO now who's saying, we want to move to Kubernetes on the cloud. That technology is 3-4 years old. Every year you get, 50 different JavaScript libraries being built? We've got a fun one here. I like this one. JavaScript tooling settles to merely chaotic. Things are changing faster than ever. So these techniques to keep up with change, I think are more and more important. So by creating options, we not only reduce risk, but we can take advantage of this volatility. Having more options is actually more valuable when things are changing faster. Back to the story. You didn't think I'd forgotten the book, did you? So you throw that magic box in between the walking skeleton and the content store. A villager approaches and exclaims, "This beautiful content I see in front of me seems to take an awful long time to get here. You must somehow make the content arrive faster. If you have a HTTP cache in your inventory, you may use it now." And we've got two options. We can place one of two bets: cache in between our content store and our content service, or cache in between the walking skeleton and our content service. We've got a very noddy diagram here. This is sort of what we had. We had our sort of templating process, a computationally expensive service using the best functional programming language in the world. Don't let anyone say Clojure's better. XSLT all the way. We've got a bunch of XML in S3. And the problem we found is, going back to the fitness functions for performance, for throughput, for page load, is these were our requirements for page load. 0.8 seconds first byte, anywhere in the world, and 1.5 seconds for full page load. And what we found with our walking skeleton in a production-like environment by running some tests was at the time, our page load looked about 35 seconds. This is bad. For the mathematicians in the audience, you can back me up on this. 35 is greater than 1.5, right? This is what we found initially when we started running tests. So we have this idea of putting a cache somewhere in this pipeline, this rendering pipeline. Again, looking at our sort of diagram, we found this problem at this particular point, and we have a number of different things that we can do. How do we decide what to do next? Let's just add a cache. So we could put it here, or we can put it somewhere else. Now, so the problem with science publishing is it's not like other media, right? So other publishing types. So things like news, right? The content for news is newer content content published today is much more likely to be accessed. You've got this a really nice sort of corpus of cacheable data that you can stick somewhere, which you'll get a massive performance benefit from caching. The problem with academic papers is that more or less, you're more or less likely to access something or cite something from 50 years ago, or 20 years ago, or 30 years ago, than you are from the current issue of a journal. Which means more or less, all the content that we have in S3 forms just one gigantic long tail. Right? There is no, you're not able really, well, we could later on predict using some predictive algorithms, but at the time we couldn't work out which of the content was going to be more likely to be accessed, so which we should cache. So essentially what we had is this problem where most of the time, for this type of content, this type of content, cache hits are not going to predominate, and in fact cache misses are going to predominate. So this idea of, yay, let's just add a cache. I'm going to go back to this quote. You have to have this quote. There are only two hard things in computer science: cache invalidation, naming things, and off by one errors. Boom. And a bonus joke for you, if you've come across this one before. There are only two hard things in messaging: two exactly once delivery, one delivery order, and two exactly once delivery. That's a free one for you. I guess my point is, we've got this weird shaped content, plus caching is hard, fundamentally. Cache invalidation is fundamentally hard. So let's just add a cache, said no one ever, basically. I'm going to go to the subtitle now to unpack it. And again, back to my physics geekdom. Anyone know who this is? Feynman. Yeah, this is Richard Feynman, who was also at Los Alamos, but wasn't included in those 13 Nobel Prize winners he was playing poker with because he hadn't won his yet, which is terrifying again. So he's got my favorite description of what science or scientific method is. In general, we look for a new law by the following process. First we guess it, then compute the consequences. Then we compare the results of computation to nature, and if it disagrees with experiment, it is wrong. In that simple statement is the key to science. And I like the fact that he goes on to say, it does not make any difference how beautiful your guess is, it does not make any difference how smart you are, who made the guess, or what his name is. If it disagrees with experiment, it's wrong. This is from his lectures, The Character of Physical Law. And I think this is a beautiful description of the scientific method, the heart of science. So what does that look like in terms of running experiments on our own software? This is the hypothesis-driven software architecture piece. So first of all, we need to observe nature, then we need to make a guess, then we need to compute implications of that guess, compare that with nature, and draw our conclusion, rinse and repeat. What might we need in order to do this? Well, we'd need to be able to observe what our systems are doing. We need to be able to observe metrics. We need to be able to make a guess, make a small change, measure the results, and ask, was I right? Did my change, does my hypothesis hold? And in terms of what we need to do for our systems and our software architecture to enable placing small bets and hypothesis-driven architecture, I would argue you need observable systems. We all need brains, which is kind of mostly fine, unless you're on a team with me, in which case you might have to use your own. You need the ability to quickly deploy small changes, and fundamentally to be able to change the things that are hard. Again, coming back to the beginning, those things that are hard, things like hardware, deployment topologies, where I'm going to put stuff, what size of machine. We need some form of lightweight probe to be able to run experiments. So, what are these practices that enable these small bets to be able to create small hypotheses, and then make small changes to be able to test those hypotheses? Well, I would say the first thing, observable systems and good monitoring. But what do we mean when we say monitoring? I'm going to credit Dan North with this definition, because I really like this definition, because you can unpack monitoring to mean many, many different things. So I'm going to use this one. We mean instrumentation. That means our code and hardware describes what it's doing. Telemetry. We need some way of getting that data from our services to us. We need to be able to visualize that data, so we can meaningfully visualize our system's behavior. And then we need to be able to alert off it, if we're in production-like environment, so we can take action based on this information, and then potentially do predictive alerting. So this is like the, the bonus one. So when I say instrumentation, what does that mean? So I would argue that for every single application composed of one or more services, we should do this as a minimum. We should be gathering information on request latency. We should be looking at service health. We should be monitoring services downstream dependencies. We should be able to say, not just am I okay, but are the things I rely on okay? We should be collecting operating system metrics. We should be doing things like request tracing, especially in distributed systems, using correlation IDs and so on. So this is the sort of minimum set of things I would expect to have in a set of services that I would build. The minimum set of instrumentation. And on this project for the science publisher, this is the sort of stack we used. It's a bit out of date now because this was from a couple of years ago, but we were using graphite to do visualization, Hystrix for circuit breaking, we were using CodaHail metrics in DropWizard, we were using Chaos Monkey to do chaos engineering, break stuff in production, Tenacity for circuit breaking, and we were using BreakerBox in Yammer. And just some examples of the sort of dashboards we would be using. So this is a graphite dashboard for a bunch of stuff. So this is for the transformations, those XSLT transformations. We actually had methods wraparounds, essentially as aspects that would tell us how long each of those things took. And this is our circuit dashboard, which shows us how the latencies and so on of every single external call in our systems we're making. That's the first thing, observability, good monitoring. The next thing, continuous delivery. These are the three monkeys of continuous delivery. So we've got Dan North, Sam Neumann, Jez Humble, and for a bonus, we've got Dave Farley popping in at the corner. This is a dinner I was at with them. And this is the original set of authors, minus Chris Reed, of the continuous delivery book. But of course, Sam and Chris and Dan dropped out because they're lazy, basically, and left Dave and Jez to do the hard work. So when I say continuous delivery, I don't just mean continuous delivery of functional requirements, user stories through into production. I mean continuous delivery of everything in our software systems, right? So all the things that we should apply continuous delivery to. We should have build pipelines not only for the functional code that we're writing as a result of implementing a user story, but also of our, non-functional code, our infrastructure code. We should have build pipelines for all changes. I guess probably Daniel spoke about this quite a lot yesterday. But very simply, a typical build pipeline would look like that. Hey, it works on my machine, check in. An artifact is created and passed down a set of automated build stages where successively more testing is done. And this applies again, functional code, non-functional code. And we get more prod-like and less prod-like, and get faster feedback. So we had pipelines for infrastructure as code on the ThoughtWorks tech. Do you want me to go back? There's photographs behind you. Yeah, that's blank screen was not working, is it? There you go. So we had pipelines for infrastructure as code on our technology radar a couple of years ago, and again, this is the technique that we, of applying the same disciplines that we do to the user stories we are implementing to infrastructure changes. Pipelines for infrastructure as code. Because if you get all that in place, right, you're able to start going through this loop, making changes to not just the features that you're writing, but to the stuff that's really hard to change. If you've got a safe, automated way of deploying changes to the things that are hard to change, as we said at the start, and you can do that in hours and minutes, you can go through this loop really fast, that changes the way I think about software architecture, the malleability of the system as a whole. And if you maybe don't think this is that important, even if you don't go on to run all the experiments and things, actually, if you look at the information in the State of DevOps report, and there's a great new book out, Accelerate, by Jez, Nicole Fulks and Gene Kim, about, the science of lean, basically. They find in that high IT performers, this is correlated with essentially a stock market performance, right? So high performers, deployment on demand, multiple deploys per day, lead time for changes less than 1 hour, mean time to recovery less than 1 hour, change failure rate 0 to 15%. Right? So if you can go through this loop, both for your infrastructure and for your features really, really quickly, it's strongly correlated with market performance. So the next thing, lightweight probes or lightweight performance tests. Now, when I say this, I'm not talking about the sort of gamut of techniques for performance testing out there, and I appreciate that this is a discipline that deserves an entire 3-week conference in and of itself. So I'm not talking about so-called load testing or stress or ramp up and all these different things. I'm talking about this idea of simple performance trending. So having simple tests run as part of your build. Again, this is from the ThoughtWorks radar, a technique. And I like to have this sort of simple performance test run on every commit within 2 weeks of starting the project or starting a program of work or starting to build a product. And so what do I mean by simple? Well, it doesn't get much simpler than these tools. Apache Bench, really, really simple. Things like Siege, again, just a command line tool, or Vegeta. So really, really simple tools that you can just run as part of your build, or you use on the command line to run experiments. I think the next thing you need is, as we touched on at the start, cloud first is a thing now. So cloud native infrastructure as code. So my colleague Keith published this book, Infrastructure as Code, last year, and again, this tied in with this pipelines for infrastructure as code. In our stack for this publishing house, we were running AWS, Botto. Running on AWS, we're using Botto as a binding to talk to AWS, using Ansible and Jenkins. But there are other techniques that are pretty useful. Things like canary releasing. This is where I'm able to spin up an entire new version of a thing next to the old version, but only direct traffic to it when I choose, or only direct a certain type of user to it, and that might be internal users, product owners, developers. Things like Phoenix environments. The ability in code to define everything about an entire environment and then click a button and have the whole thing just come up. Not just a service being deployed, but all the things we need, all the firewall rules, all the IP table rules, all the networking rules, who can talk to what, all the autoscale groups, everything coming up, Phoenix environments, and then tearing down. And another technique closely related to canary releases are blue-green deploys. And this is an example. This is an animated GIF of a blue-green deploy on this program, which is pretty cool. So this is where we deploy, well, the gray is an old version of a service, of actually a cluster of services. The blue is the current version that's receiving traffic, and the green is the new version. And so what we're seeing, so what we're seeing is a switch in DNS that is switching to all the new versions. And this brings me to an interesting point, which is more and more these days, production doesn't have to be live. We've moved away from the idea that we've got one data center, we've got expensive machines in it, so we'll have a live environment and we'll have a test environment. All right, these days, production and live don't have to be the same thing. We can deploy into a production environment, but things only become live when we direct traffic to them. And there's a distinct difference between these two things. And the consequences are being able to use these techniques. So good monitoring, a brain, the ability to quickly deploy small changes, lightweight probes, putting it all together. And if you're easily offended, I'd cover your ears now, AKA, gonna have to size the crap out of it. So if we go back to where we were, right? So we had this 35 seconds page load time on our system that's in production-like environment. And we need to get
We have plenty of time for questions, so
Yeah, I had a question with the finding conclusion that if things don't agree with the experiment or experimental results, it's wrong. Because it seems like a lot of times it's close. How do you get off like it's close versus it's wrong?
Sorry, I'm going to back up. So this is going back to Feynman's statement that if it doesn't agree with the results of experiment, then your guess was wrong. So can you give me an example of where it might be close?
Like the caching example, maybe
Oh,
it seemed very close. Like you did get some benefit, but ultimately it was wrong, and you had to choose a different caching.
yeah. Yeah, okay, great, thanks for clarifying. So the question is, what happens when these bets lead to similar outcomes, actually? You could choose very similar outcomes, and it's not obvious whether actually the thing that you've implemented was the right choice. Because it doesn't become apparent until further hops down the line often. Which is why making small changes is good. Because even if it's a couple of hops down the line, you can still go back. Right? You can still revert, you can still play a different path. So we were lucky on this program because we set up a kind of, I guess you'd call it, the hipsters would call it a site reliability engineering team, whose responsibility was, part of their responsibility was to help the other teams look at performance and look at this sort of stuff. And so there was a stable group of people who were both sharing knowledge about this and doing it themselves, which made that sort of thing safe to do, to roll back from multiple steps. Sort of thing. So, if there are no other questions, I'll be around. Oh, yes.
So when you were mentioning the blue-green deployment, I heard like you switched the DNS to doing the blue-green deployment.
Yeah.
Did you have like problems with like the DNS servers updating especially when you don't control the services? Like if something goes wrong in the new environment, rolling back may take longer. Like you never run into this?
So the question is that it was a clarification about whether for blue-green we were using DNS to route traffic, which we were. And did we ever experience problems with DNS timeouts? Specifically with the JVM, we did, yes. But they were so rare. I mean, I think it was one of those situations where that's the one thing that we were worried about before choosing to use DNS to do the traffic switching. But actually, because we had all this monitoring in place, we had these tests running, more or less continuously, people looking at this stuff. We pretty much ran that experiment, and it worked. And when I say worked, the number of errors that we were getting was very, very minimal, well within what our business, product owners were willing to accept, like hardly any. So it was one of those things that we were worried about, but then actually it didn't manifest in real traffic. Maybe it's I don't know. Maybe it's an example. I get quite fixated on things being perfect, and actually that was good enough, and that was good enough. Yeah.
Can you go back and look at some of your older decisions and decide that more recent decisions made those unnecessary?
That's a good question. So did we go back and look at our old decisions? One of the things I didn't mention, and then did we work out whether they were unnecessary or not? One of the things I was going to put in this talk but didn't, because which might have been useful for this community, was around patterns and where do pattern languages fit in with this solution space stuff. Because of course that's the shortcut, right? The shortcut is to use a set of patterns that we all agree are kind of useful patterns, which we're doing, circuit breaking, bulkheads and all that sort of stuff, to say we don't have to start from scratch every time and roll forwards. Actually, we were at a baseline, we're sensible, experienced people, we know this stuff. But it's still interesting because I think even from that baseline it becomes sort of fractal. Actually, because it's after the patterns are applied that you make money, right? Unless you're selling a product and you're selling exactly the same product as how do you differentiate yourself unless by the decisions you make after you apply patterns, if you see what I mean? Yes, I think there is opportunity to look back, and actually these decisions should form the basis of a set of patterns. But there's always going to be a set of stuff at the top that is going to be the stuff that differentiates you from everyone else and makes you money. Does that kind of make sense? There's also, I'm going to shout out to Mr. Nigel over in the corner. One of the things I also wanted to put in this, which I didn't manage to, by the way, I do tend to waffle when I answer questions, was how this links with architecture decision records. If you haven't come across architecture decision records, there's a great blog post by Michael about using them as a very lightweight way of capturing the results of decisions you've made. And the great thing is they live in your code base. So over time, you get to, especially for things like onboarding new team members, you get to point out, oh, this is why the build file looks like this, or this is why the cache is in this place. So I sort of think there's like a nice, it's almost like a tie-in between the idea of the options, the set of options, and the option you choose, leading to an architecture decision record that stays in your code base, which can be mined over time. I don't know if that's something that you probably do that in Cognitect. Yeah. Yes, he's awesome. And the second edition of his book is out and is one of the best things I've ever read. So there you go, just saying. He's also blushing now, which is cool. Sorry.
What's the approach that you use for testing your infrastructure as code? More like black box, or you have like any unit tested components?
So bearing in mind this was quite a few years ago, and so the tooling wasn't where it is now. There's a bunch of like service spec and stuff this is maybe 3 or 4, when was it? 2014. This product is still running, and they're still building on it. So at the time, it was, what the hell was it? Chef, no, it was, there was one that we were using to test the Ansible scripts. I can't remember, if I'm absolutely honest, sorry. Yeah, I can probably dig out, I've got the code on my laptop, so. But these days, things like service spec are the kind of default standards, I guess.
Then I guess it's time for lunch.
Thank you very much.